Okay, so yeah, my name's Mark, and I'm going to recount a project that I worked on where we rewrote petabytes of data into Apache Iceberg format using Trino as the compute engine. And you can see Commander Bun Bun is dressed as a penguin on an iceberg. So a little bit about me. I'm Canadian, if you can tell from my accent, I don't know. I'm from Toronto. I've worked in the data space for about 6 years, and in my spare time, I swim in a lot of pools. I've actually swam in the bay before, very cold. Okay, so let's go over the agenda. So I'm gonna outline the problem statement and give you guys some context on why we were trying to migrate petabytes of data. That's not something you would want to willingly do. It's not that fun. Why we thought Iceberg was a good solution for our problem. I'm gonna go from a high level, different migration strategies you would want to consider if you found yourself in a similar situation. Then I'm gonna go over the Trino Iceberg integration. I'm going to go over some benchmarking results between old and new data sets, and then finally I'll go into some reflections on the project at large. So let's start with the problem statement. So I work at Shopify. I'm on the Lakehouse team. The Lakehouse team has two generalized mandates. The first one being to ingest all the first-party data sources, and the second one being to optimize the storage and retrieval of that first-party data. So if we look at the Lakehouse data assets or data sets, we have our raw data here. And the two event data and CDC data, that represents the first party data. So CDC data, change data, capture data, represents the data stream of all the tables that back the production applications. And then we also have event data, which is basically anyone at the company can spin up a new Kafka topic is really what it is. They can submit events to that topic, and we will materialize that in our data lakehouse. So, this is all good and fun. The lakehouse, we store these tables using the Hive table format. And yeah, it's all good and fun. But if you work in the data space, you might realize that we're missing a huge part of the data assets of the company, and that is model data. And how Shopify kind of evolved was that new tools were spun up, and the tools were specific to the language that modeled the data. So we have one tool that specializes in SQL-based transformations. We have another tool that specializes in Spark-based transformations. And then we also have a myriad of tools which specialize working with BQ or BigQuery datasets. And if we take a step back and think about all the different table formats that are at play here, we have at minimum 3. We have the Hive table format. We have a proprietary table format, which is BigQuery. And then, unfortunately, the tools here, the SQL and Spark tools, they actually invented their own table formats, which is really fun. So if you then think about that from a architectural standpoint, what it will look like in practice, you get this. So you get all these tools, and they read and write, sometimes in their own made-up table format. And let's say you want to spin up a new tool. Best case scenario, you have to write adapters to every single tool that you want to work with. So, we have data scientists that would come to us and they'd be like, I use tool A, I produce dataset B, and I want to use that in tool C. And they say, how do I do that? And we're just kind of awkwardly looking at them like, that's a very reasonable request, but actually it's very hard to do in practice. And it's not like we designed this architecture here. It's not like this was the intended outcome. We actually just kind of sleptwalk into it through an intense period of scaling. And it doesn't really take a genius to think about what the idealized kind of architecture would be. It would be that every tool has a standard reading and write format, and it goes through the lakehouse, so we have centralized data assets. And so we took a step back again, and we were like, okay, what do we want all our centralized table format to be in? And we decided we wanted to write it in Iceberg. And this is really, I think, an easy decision to make currently. And so I'm just going to go over like really quickly what an open table format is, in case this is like the first time you're ever hearing about it. I know it's kind of challenging for me to kind of understand what it was actually doing when I first started working with them. So at a very like simplified level, all table formats are doing is they're libraries that keep track of files that make up a table. And so a colleague of mine kind of came up with this analogy, which I actually find very useful. And it's that the abstraction the file system places on a hard drive is kind of like what a table format such as Iceberg is doing on an object store. So you're storing in a file system, you're storing all the actual data on the hard drive, but you don't need to know where it is on the disk. That's what the abstraction of the file system does for you. And it's the same thing with something like Iceberg. You don't need to know where all your files are. You don't really even know how to relate them to each other. That's what the library of Iceberg will do for you. And so I would be remiss if I didn't show you the Iceberg spec in a diagram, and this is it. So you can see that it starts off with metadata files, which track the data files down here. Now, I think what kind of confuses people is that you talk about like the Hive table format and then Iceberg table format, but then when you look at your architecture, you still see Hive in it, and that's because you still need a metastore. And so typically someone would use a Hive metastore. So even though we're changing our table format, we still have Hive in our architecture. One really cool thing that I want to bring up about Iceberg is it introduces this idea of snapshots. So you can see here we have our snapshot 0, and then our table gets evolved. Maybe data was appended, maybe it was deleted, whatever you did. We have a new snapshot. So our table is kind of like evolved, and it's kind of starting the underpinnings of bringing Git-like semantics to data, which is something I really looking forward to in the future. I think that's all I wanted to say. Okay. So, we made this like really pie in the sky vision. We want to bring our data lake to Iceberg, use that as the ubiquitous table format across the org. And, everyone's thinking like, yes, I get to write my new data in Iceberg format. But then you kind of have this like stalker, behind you holding you back, which is all your old data, which is actually most of your data, right? So it kind of like, we convinced senior leadership to, invest resources into this, and then we finally got them on board, but then you're like, crap, now I actually have to build it. So we decided to start with one use case. So remember, this is like all our data assets. We decided that we were going to try and migrate our event data first, and remember that this is currently being stored as a Hive table. Now, a dirty little secret is the file format is really bad. It's actually being stored as JSON, and it is columnar data. So it's really not performant, but that's why we're going to migrate it. And so there are different migration strategies you might find yourself employing if you want to do this migration. And so I just outlined kind of 3 of the major ones. One thing about the difference between like Hive table format and Iceberg table format is they don't support the same types of files. So, well, that's not, I guess, entirely true. Iceberg supports a more restrictive number of file formats. So whereas Hive, it was perfectly happy supporting JSON file formats, Iceberg, you can't do that. Iceberg only supports Avro, Parquet, and ORC files. So if your data is not in one of those files, guess what? You get to rewrite everything. And that's all the data, and that's really expensive, right? So you want to try and avoid that if you can. So let's say your data is in a supported file format, so let's say it's in Parquet, but you want to change the partitioning strategy. That means you have to rewrite the data because you want to change how the data is represented on disk, rewrite everything. So let's talk about the last one, which is kind of the one you want to be in, is that your data is already in a supported file format and is already properly partitioned. That means you get to just generate the manifest files, which is actually not that expensive. So if you get to choose anyone, or if you want to be in anyone, you want to be in this last one, but we were in this one. I said they were in JSON, right? So we have to rewrite everything. Okay, so this is the top architecture of the system that we decided to build to rewrite everything. You can see that we have a table manifest. So our event data, we have about 5,000 plus tables that we're trying to migrate, and they range in size. Some are like not even a gig, some are multiple petabytes. So what we would do is we would take that table manifest, we would feed it into a Python file. That Python program would basically generate a DAG per table. So you can, that's what I'm like showing here is the DAG per table. If we like blow up into one of the DAGs, this is what we have. We have a rewrite job. The DAGs are actually just single nodes. It's a Kubernetes pod operator that just kicks off a Python script. That Python script has 3 major tasks that it does. The first one it does is it does a diff between the old table and the new table, and it figures out which partitions don't exist in the new table yet. It takes that list of partitions and fills the queue. Then what it does is it starts up workers, and those workers start submitting queries to Trino to migrate partition-wise the data set. After the partitions have been migrated from Hive table format to Iceberg, we'll do a reconciliation, so making sure that we didn't mess up anything in the migration process. And then we'll store the results of each partition for each table to make sure that we've audited each one so that we can be confident when we deliver these data sets to whoever uses them. Okay, so let's revisit our agenda. I've gone over the problem statement, why Iceberg helped us solve a huge problem. I talked about different migration strategies that you might want to employ if you want to do this as well. And now we're going to go into the Trino Iceberg integration. So what was really cool about this is we actually kicked off this project, and I would say at the time, Trino wasn't really the obvious compute engine to use. I think most people would have used Spark. But we actually had someone on the Trino team at Shopify working on this project with us. So they're like, let's use Trino. And we're like, sure. So, but it was really cutting edge when we started working on it. So we actually started hitting blockers along the way. And then what was really cool is that people in the open source community were like making PRs that were solving our issues like in real time. So that was like really cool to work through. And I'm going to go over some of those blockers and the solutions for them. And I'm going to call out the people that actually fixed them. I am not a stalker, though, I promise you. OK, so the first one actually was fixed before we started this project. But it was that the Trino connector was having trouble reading partition data sets that were partitioned on timestamp with time zone. And so remember, we're just reading off a Kafka topic. So it's very common for people that are ingesting stream-like data to partition on timestamps with time zones. So that's what we were doing. And there was actually this error. It just didn't know what that type was. So this lovely fellow here, Piorto Fienscenes, sorry if I butchered that, submitted a PR in PR 9757, and it just returned the correct type. And so we were off to the races there. So okay, then this one we actually hit in real time while it was happening, and it was PR'd kind of within the same week. So we built our first system, or our first go at the, at the software, and as I said, some of the tables are massive. And so if we just let it go sequentially by partition, it would have taken like years. Like obviously we don't want this project to last years. And I think what most engineers would do is just throw concurrency in and set up a bunch of workers. And so that's what we did. But then we started getting this error. And what it says is it's saying that the commit failed exception. It's saying that the metadata location of the table is different than the one that it's trying to commit on top of. I know that probably didn't make much sense, so I have a diagram. So let's say that we have our table, and this is the snapshots. So we have snapshot 0, snapshot 1. Iceberg operates under an assumption of optimistic concurrency. And so if we had 2 simultaneous processes trying to append on our table, they would both be using snapshot 1 as kind of their node before them. And so eventually one would actually succeed, and now the snapshot went to snapshot 2. But this commit is still referencing snapshot 1. And so that's what the error is really telling you. It's saying that, I'm not committing in sequence anymore. I'm referencing an old table that doesn't really exist anymore, so it doesn't actually work. Now, Iceberg actually does have support for retrying, and what's really important is that when you do this retry, you don't want to rewrite your data files. Remember, that's the most expensive part. Rewriting manifest files is actually pretty cheap, so if you actually hook into the proper error statement and retry cycle of Iceberg, that's what will actually happen, is it won't rewrite the data, it will just rewrite the manifest file, and you'll get a good commit, it will succeed. So this, as I said, we hit this error in real time. We were like, oh crap, maybe we should have just written it in Spark. But we were like, let's just take a breather, let's take a couple weeks, work on your other projects, let's come back to this and decide what we want to do. But in that time, literally in the 2 weeks, this guy right here, Alex Joe, he submitted PR 11886, which threw the proper error, which hooked into Iceberg's commit retries. Okay, the next problem. This is not unique to Trino. If you work in Iceberg, you're gonna hit missing file problems all the time. So basically what happens is, like I said, your table's evolving. It's not a static asset. And if you're managing lots of tables, really big tables, you're gonna be cleaning and maintaining that table. You're gonna be expiring snapshots. You're gonna be compacting files to make them the optimal size. So your tables files are really moving a lot. And it really leads to an opportunity for this error when maybe you deleted something and you weren't supposed to. It actually was supposed to be part of the table, but you deleted it. So now your table's in a corrupt state. And if we think about the architecture, right, we have an object store, so that's S3 or GCS. We have a Hive metastore. We have Trino. And they're all talking over network. So there's a lot of opportunity for timeouts, right? And so basically what was happening was Trino was trying to be nice. It would submit an append or whatever it was doing to the table, and it wouldn't work. Maybe the network timed out and it would fail. It would think it actually failed, so it would try and be a good citizen, and it would go and clean up after itself. It would say, oh, I tried to commit that file, but you didn't actually work, so I'm gonna be a good citizen and delete it for you. Don't do that. There are cleanup procedures, orphan file cleanup. It's way more expensive to fix a corrupt table than to just have a file there that actually isn't a part of the manifest list. So if you do that, it's way better to just leave it and let Iceberg clean it up for you than you trying to be a good citizen. And so this PR, Marios Grama, on September 16th, this was actually just last month, fixed this. Now, like I said, missing file problems are very common when you're working with Iceberg. So we actually had this other hacky system in place. I'm just gonna quickly go over the architecture because you'll probably, if you do dip your toes in Iceberg, you will run into it. So our kind of hacky fix was to, on our object store, have a lifecycle policy to keep the deleted files around for 14 days or whatever, configurable amount of days. And then we had this other procedure that would crawl the manifest list, and if you were referencing a file that no longer existed, it would just recover it. And so that was our hack fix, but like I said, this fine gentleman created this PR to actually fix it the right way. So that's nice. Okay, I'm talking very quickly. So benchmarks. Okay, so I'm going to go over some benchmarks of the tables from the old state to the new state. I'm going to show you 3 metrics. There's a bunch of other metrics. I just chose these ones. There's the planning, there's the cumulative user memory, and then there's going to be the runtime, which is a you could use as a surrogate for CPU cycles. I guess, don't at me if that's wrong. Okay, so this table, the first table is our checkouts table. So Shopify, we host stores. You buy stuff online. So we have this table that is every checkout ever. It's 153 terabytes large, which isn't that big, but whatever. These benchmarks were done on using 60 workers of N2 standard 64 machines. We're on GCP. And you can see that our Hive plus JSON compared to our Iceberg Parquet is just like so much faster. This is about like a 25 times speed up. In planning time, again, we get a similar type of speed up in cumulative user memory. And we get a similar type of speed up in execution time. So this goes from running and taking an hour to taking 3 minutes. So I just want to let that sink in. Like if you're a data scientist, like they love Iceberg, right? They're, flow state, I'm sure engineers here, you know what being in flow state is like. Imagine submitting a query, having to wait an hour for it to come versus 3 minutes. You can stay in that flow state. Let's say it errors. You don't have to wait an hour for it to error. So another really big thing is the cumulative user memory. I love Iceberg, obviously, but I really think that this is just more of a function of doing the JSON to Parquet migration. Because it is columnar data, when you're working in gzip JSON, it actually does have to unpack it, which is why it takes so much memory. Whereas if you actually use a columnar format like Parquet, you can actually leverage it and get much better results. So this was just like a simple select query, no modeling on the table. I came up with my own simple model, and I decided I wanted to know what what shop had the most checkouts in the last 30 days. So what is the most popular shop? So it's a little bit more of a complex query. It has a group by, has a sum. And again, we see a huge improvement in planning time, huge improvement in user memory, huge improvement in execution time. So you might be wondering, Mark, why is this so much fast? It's only half an hour and sounds like it was more complex. Remember, I only did it for the last month, so 30 days. I'd just like to say, maybe if you're a cynic, you might be like, Mark, did you rewrite your queries to make use of partitions in the Hive tables versus the Iceberg tables? I did not. I used the same query, okay? I thought about doing it, but I didn't. Okay, so this is going to be the last benchmark. This is on one of the biggest tables. So this table itself is over 1.5 petabytes large, just one table. It is the table that tracks, so Shopify has a public API that anyone can use and build apps off of. And so it's a GraphQL API. So this, I came up with this trivial naive model. I decided to look at what was the most used schema or endpoint in the GraphQL API in the last 30 days. So you can see, again, huge improvements in both planning time and cumulative user memory. But look at this execution time. 3 hours to 1.78 minutes. It's 1,000 times speed up. Okay, we're at the end here. So I'm just going to go over some reflections and advice that I took away from working on this project. Really show, I think the benchmarking really shows the utilization and the power of utilizing modern table and file formats. If you have data stored in text files and JSON files, migrate it. Your users will love you. I want to say that there is a huge benefit using open source software here. And I would say, like I've mentioned a few times, I think typically someone doing this project would have used something like Spark as the compute engine. But if we ran into issues in Spark, I don't think we would have actually had people help us and really PR changes. The amount of activity that's actually in the Trino Iceberg connector community is really beneficial. So it's actually really good to make use of that. The missing file bug, I'm pretty sure I was the first one to report that, and I actually had some people's eyes pretty high up in the ranks of Trino looking at it and interested in it. And you're just not going to, at least in my experience, you're just not going to get that if you were to use something like Spark. Okay, so this is maybe a little abstract, but So you're rewriting the historical data. You have your new data being streamed in, right? Our initial idea was that we're going to write them to two separate tables, and we'll stitch them together using views. Now that worked with Trino, but we had a hell of a time getting that working with Spark. And even worse, like why now I have to maintain two separate views of the same thing. Like Apple, I think, mentioned, global views can't come soon enough. So anyway, if you're going to do it, like I would just suggest, if you can, write them to the same table. It's just going to save you a headache. You're not going to be managing two different representations of the same thing. So that's something that like we kind of figured out really late on because that's actually the last step of the project. So that was fun. I would suggest and recommend that you should construct a migration priority list. So like I said, we had like 5,000, 6,000 tables that we were migrating. At first, it was really easy to choose which tables to migrate because there was people who were like, I have to wait 3 hours for my query. So it's like, yeah, you're getting migrated. But after a while, it's kind of like no one's actually noticing that their performance is crap. They're just like, you know, their jobs are running overnight while they're sleeping. They don't really care. But you know who will care? The people at your company that run Trino. They'll care. So what we did is that team actually had every query documented in the Trino footprint that it put on. So what we did is we used that data to construct a priority list of which ones will actually get the biggest like reduction in Trino footprint. And that was really helpful for like, just constructing the priority list. So my last kind of reflection or maybe advice is if I was to redo this is, Airflow offered a really nice out of the box like management for these jobs. But ultimately, like I said, some of these tables are really long or really large. And so the Airflow process is really long running. Airflow doesn't really like managing a job that might take weeks to complete. So if I was to redo this, I would probably just like write my own software to like kick off jobs, track jobs, shut down jobs, like my own little job scheduler, nothing fancy, but like something that wouldn't have just like caused zombie processes. So yeah, that's the end of the talk. I just want to give a shout out to the two other devs that worked on this project with me, Sam Weeding and Victoria Bukta. And that's it. So I think we have like a little bit of time for questions, if there are questions.
Does anyone have a question? Oh.
No hard questions, that's my only rule.
Should I go or someone else? Yes. Okay. How did you guys stitch Trino and Airflow together?
So we use Jinja templating, and we just use the Trino, like the Python package of Trino, and you just set up a connection, like with the config, Trino auth. It's like a Python package. Okay. And you just like auth through there, and then you just can submit queries through like a database cursor kind of thing.
Gotcha. So you guys use the extension, the Airflow extension?
No. It's just like the Trino library, like the Trino Python library. I can show it, like pip install Trino, and you have it.
Gotcha. Okay. Cool. Thanks.
Kind of on that same, wow, it's loud. On that same note, when you were doing writes, what were your write speeds? Were you able to get? We have almost the exact same backend.
Remember, I said no hard questions. We didn't actually measure that. Okay. I'm sorry, but that's a very good question. Like bytes per second. Our director actually asked us that, and we we're just like, yeah, it's working. That's a good question, though. We should have done that.
How do you write the new incoming data into the table? You had like one line that said, write the new data, the old data to the new table, or whatever. How do you actually do that?
That's a very complicated question. So that's a different system, right? I said like our two mandates. One is to storage and retrieval. The other one is ingestion. So I said Vicky Bukta, she has talks that are specific on that system. But basically what we did is we wrote a Kafka plugin, and it just like streams off the Kafka topics, writes them into files. Then we have another thing called async committer, because you would get commit contention on your table, and it will register those files on your table. Thank you.